There are some additional approaches to simplifying rational expressions. Sometimes they might not factor, or sometimes when they do factor, there's more that we can simplify beyond just factors like we normally see them. So we're going to take a second to look at these two new approaches. In the first one, approach number 2, we have 7x to the 5th over 21x squared. I don't have any polynomials with multiple terms. These are both what we call monomials. There's only one term in each. So we can't factor anything here, but we are going to still simplify it anyway. Step 1 is going to be to list the domain restrictions. So by looking at the denominator here, we have 21x squared. So I know that the denominator cannot equal 0. And if this is multiplication, then the only number I could plug in to multiply to get this denominator to equal 0 would be 0. So I know that the domain restriction is that x cannot equal 0. Now you can always set it equal to 0 and solve just like we've been doing before, and you should get the same answer. Then we're going to simplify the variables by looking at the exponents. Okay, we've done this before with exponent rules. If I have x to the 5th over x squared, how would these simplify? We can divide variables that have the same base, so they're the same variable, to different powers by subtracting their exponents. So x to the 5th divided by x squared, well, 5 minus 2 is 3, so we would get x cubed. But there's a hint here because sometimes the x doesn't always end up where you expect. So hint, wherever the bigger exponent is where the variable will end up. So here we've got x to the 5th in the numerator. That means when I simplify, I get 5 minus 2 is 3. So we get 7 over 21, and x cubed goes up in the numerator with the 7. Then in step 2, simplify the coefficients like you would a fraction. So almost ignore the x's now and just look at 7 over 21. Would 7 over 21 reduce? Are they both divisible by the same common factor? 7 and 21 are both divisible by 7. So when I simplify that fraction, I get 1 over 3, but don't forget to bring your variables along. So we get 1x cubed over 3, or you can just write that x cubed over 3. You don't need the 1. Before we move on to approach number 3, let's do an example of this approach here. Example 1. This might also help you understand the exponent rules a little bit better as well. So I'm going to start step 1 by listing the domain restrictions. Now in this case, I have 2 different variables in the denominator, and so it's really important that none of them make the denominator 0. Because it's all multiplication, I know that my restricted values are that x cannot equal 0 and also that y cannot equal 0. Even though they're being raised to exponents, still, 0 to any power is 0. Multiplying by 0 is not good. The next thing we can do is simplify the variables. So let's start with the x's. So I've got x to the 6th power over x technically to the 1st power. We can imagine the little 1 that's there. So when I reduce these, x to the 6 over x to the 1, we do 6 minus 1, which is 5. And the bigger exponent, 6, is on top. So we know x to the 5th is going to go on top in the fraction. Then we can look at the y values. We have y squared over y cubed. So we have 2 and 3. Well, 3 minus 2 is 1, but 3, the bigger exponent, is in the denominator. So that tells me that y to the 1st power will go in the denominator. Then we're going to look at the numbers, 2 over 12. What are 2 and 12 both divisible by? Well, they're both divisible by 2. So 2 divided by 2 is 1, and 12 divided by 2 is 6. So here is our final simplified form, and here are the domain restrictions. Let's go over approach number 3 now. So in approach number 3, I see a fraction like x squared plus 1 over x. And while the numerator does have an x squared, because it's an x squared plus 1, we know that this cannot factor. And so we're going to still want to simplify, but it's going to have to be in a different method. So step 1 is to split the fraction into 2 or more separate fractions. List any domain restrictions. When we split this into separate fractions, we split it up based on the addition or subtraction in the numerator. So because this is a plus here and there's 2 terms, we have the x squared and the 1, that tells me I'm going to have 2 separate fractions when I split it. I can split this to x squared over x plus, because it was a plus in the numerator before, 1 over x. We're basically doing the opposite of adding fractions. Do you know that you can add fractions if they have common denominators? Well, I could also work backwards and split them up into separate fractions with common denominators. Now, looking at these fractions, they both have x in the denominator, so that tells me that the domain restriction is that x cannot equal 0. Now, step 2 is to simplify each individual fraction using approach number 2 that we just learned. So like x squared over x, I have x squared over x to the first power. 2 minus 1 is 1, so we're left with just x to the first power. And it should go in the numerator because 2 is the bigger exponent. But there's nothing else in this fraction, so really we can just write x. We don't have to put it over 1. Then for 1 over x, that does not simplify at all, so that one will just stay the same, and we simplify this to x plus 1 over x. Let's try an example here in example 2. I'm going to start by splitting the fraction. Now you could also at this step look at the domain restriction as well. I can tell right away that the domain restriction is x cannot equal 0. So now I'm going to split it up. We get 4x over x minus 3 over x. I've just split it into 2 separate fractions. Now we're going to simplify what we can. In the first fraction, I have 4x over x. Well, x to the first power divided by x to the first power, those are going to cancel, and so we're just going to be left with the 4. Minus 3 over x, that doesn't simplify. So here's our simplified fraction with its domain restriction. You try the next few examples and see how you do.